Thank you all. I want to first of all begin by thanking you for giving me the opportunity and my students to work on this very important project. I consider it a tremendous honor to be able to work on this, and we have taken this honor and we are working extremely hard to provide the proper science to bring this to give you an idea of what this structure may have been experiencing on that day on September 11th, 2001. So to begin with, let me just start off by saying that I want to thank the 9/11 Truth for giving us this opportunity and speak briefly about the team. I want to kind of give you a quick overview before I get in through all the slides, and then I'll move through those fairly rapidly. So the team I have put together for this study consists of a PhD, recent PhD graduate that's worked with me for quite some time, and another PhD student who is currently working on his PhD that's dealing with the understanding of fires in high-rise structures, particularly steel structures. And that has come about because of this project and what we've discovered to be a lot of unknown variables associated with fires in major structures. So the tools that we are using to evaluate this study has to do with Abacus, which is a finite element, very sophisticated finite element program. It's a very good program. Sept 2000, which is a program by Computers and Structures out of California. It has the capability of doing nonlinear and large deformation theory capabilities, which basically enables us to do progressive collapse when we are in that process. And also SolidWorks, which we are using to evaluate the heat transfer and temperature distribution through the various structural elements, as well as looking at components of the concrete deck and its composite response to the steel framing within that building. Remember that this is a 47-story building. It's extremely complex. It was extremely complex. It was not symmetrical. There's some elements that are very confusing about the design, and so I wanted to focus today on the NIST report dealing with the fire theory that they presented regarding the failure or the collapse of this building. Our objectives for this study was to, first and foremost at the beginning, I said I probably would not be able to tell you what brought this building down, but we would focus on what did not bring it down. So, and that's where we are. Keep in mind that there's a lot of information that's not available because of it being removed from the site without us being able to have the opportunity to study it. But we do have enough through the erection drawings and various other things that we've been able to get our hands on that enables us to answer the questions that we've been focused on, which deals with what did not bring this building down. So today, I want to emphasize that we are working at this from an approach that we'll look at every aspect that we can think of that may have affected what went on that particular day, and we'll look at it from a pure scientific point of view and discard those that are not reasonable. So taking that in mind, let's start moving through the slides. This is the investigation of the collapse. The three of us that are working on it is myself, Dr. Fan Shuo, who is my postdoctoral researcher, and Zili Kwan, my PhD student. Our objectives of our study was to evaluate the findings for the collapse presented by NIST. What did not cause this collapse is what we are going to focus on till the completion of this study. Examine progressive collapse mechanisms and provide a summary of findings and conclusions. Today, this presentation, I will attempt to answer the question, did WTC7 collapse due to fire? Our approach was as follows. We first began by taking the erection drawings and the various things available to us to develop a virtual structural model. The programs we're using, as I've already mentioned, are AutoCAD to put it all into a electronic media, Sept 2000, Abacus, and SolidWorks. I put together a quality control program immediately so that we had non-disputable science to become our priority, and the team meets daily to question our findings and formulate an approach for the next step, and we do that at the end of each day. Both Dr. Shao and Mr. Quinn use different programs to solve the problem. As an example, to look at what I'm going to present to you today, we use both Sept 2000 and we also use Abacus, and they were done separately, and to verify our results to get very close to the same answers. Dr. Shah performed analysis using AutoCAD and Abacus. Primarily, the Abacus models dealt with looking at the connections, and Mr. Kwan used AutoCAD, Sept 2000, and SolidWorks. My focus is to ensure that scientific solutions are not influenced by previous research. Once the results are tested, the information will be thoroughly evaluated by our peers, and we intend to put together a peer evaluation committee prior to completion of this work. And then once that has been reviewed and scrutinized, then we intend to put it out and publish it in the literature. I want to also point out something that's really quite important here. We typically, as educators, educate structural engineers with the idea that we need to have safe buildings, make sure that the loadings are correct, make sure that we have the proper safety factors, but attention is not given to heat transfer or thermal distribution, temperature distributions. We rely pretty heavily on test data in terms of providing 1 hour and 2 hour fires and so forth. And we discovered through this process that most of that is basically wall systems and not necessarily three-dimensional structural systems. So the other thing to recognize is when you have thermal response, you end up with things like radiant heat, convection, conduction, and these various aspects are working simultaneously. And so in order to have a movement within a building or anything else, the building can literally, or any kind of structure, let's examine, for example, if I was to take just a thin rod, and if I was to heat up that rod and it was unrestrained, the rod, and it was a uniform temperature, there would not be any consequence. However, if I restrained its ends and heated it up, and if it was a piece of steel, about 200 degrees Fahrenheit would cause major problems for that little piece of steel. It doesn't matter how long it is, it matters about the fact that it was restrained. If I took a concrete deck and I was to increase the temperature, it would take about 150 degrees if I totally restrained it. But if it was not restrained, it could basically continue to move and not have a problem. That's pretty significant about what I'm going to share with you today, because there is a point where if you heat something up and there's restraints within it, it's going to move with respect to the stiffest point within something. So we looked at the material properties of the concrete, the steel. We looked at what kind of aggregate perhaps was used for this particular concrete placement. The best I could tell is it's probably a local aggregate such as a dolomite concrete aggregate. We looked at the diaphragm behavior of the concrete floor system. We looked at and examined the point of zero movement, which is that stiff point I'm referring to in the floor system. Concrete steel floor interaction, composite, non-composite, and partially composite was all examined. We looked at the influence of shear studs, and there was a big controversy about this, about whether there were shear studs at the girders versus no shear studs at the girders, so we looked at both. In every particular case, we looked at the extremes, both with and without, to try to examine what may have happened. Because this is a really complex building, 47 stories, it would take a huge amount of computer time to analyze this structure in a virtual system. So we utilized substructuring, broke the various pieces down, broke the floor down into equivalent behavior so that it would expedite the processing time and still get the same results. So we looked at the concrete floor, looking at both the fluted stay-in-place forms. It behaves differently in two different directions. Looked at the welded wire fabric contribution in it. Looked at the heat transfer through that whole system as well as the stiffness of all of that. Looked at every connection within that building. We broke it down and put springs to model the behavior of the connectors and looked at their response. And so those springs to replace those floors from 3 to 11 and 14 to 47, we examined to try to get an understanding of how floors 12 and 13 may have responded. Because, listen, today we're focusing on column 79. We looked at nonlinear springs to replace all those connection types. We looked at heat transfer, considering a drop ceiling, the fireproofing, no fireproofing, the heat conduction and resistance of each one of those particular products. So our approach, the research team, investigated the building in two ways. We examined the NIST approach, and we looked at R modeling. The numerous conditions were examined to evaluate structural response versus fire location. So we moved those fires around. I need to point out to you one thing. We did not do much about creating new fires. We used the NIST fire, the idea being that if we got their same results, okay, then we have to ask different questions. But if we did or did not have a problem with the column 79 using their models, then all of a sudden we have a big issue. So numerous conditions were examined to evaluate structural response versus their fires, and we looked at the worst fires that they had recommended, the effect of no shear studs versus the shear studs over the girders, fully composite versus non-composite versus partially composite. We looked at other conditions such as no fire protection, the effects of welded wire fabric in the flutes or in the concrete deck, the flutes, the stay-in-place forms on the heat transfer. We looked at airspace below the system where you would have a drop ceiling, but determined the fire would probably have gone in there fairly quickly if the fire was below. So some of the NIST discussion points that I want to bring out. Please focus on this slide. This slide, if you'll look at it, represents floor, in this case, floor 13. The red that you see and the brown and the black are the framing in that plan view of that floor. But the blue represents what NIST did in terms of putting and approximating the connections using springs. The portion outside of that, they did not do that. They did not put springs to represent the connections in that left space. I want you to remember this. That means that the system in the right, the blue side, is going to be more flexible than the side that's to the left in the red. Also, they didn't model the exterior framing with springs. And when I say springs, I'm saying that's a substructuring technique that we use to try to cut the computer time down, give us the equivalent of what that connector really was. So their argument was the following. They lost lateral support at the buckling initiation at column 13 because it moved, the girder moved so much as to push the column off the bearing, and as a result of then it had progressive collapse because they lost lateral support. He also said that the outside selected area connection failures were not modeled, such as a fix or pin were used. That's that red area I was just referring to you. The connections were not modeled in the exterior moment frame either. So NIST also said on 1.9, page 525 in 2008, that a girder was considered to have lost vertical support when its web was no longer supported by the bearing seat. Thus, the bearing seat at column 79 was 11 inches wide, and when that girder end at the column 79 had been pushed laterally at least 5.5 inches, it was no longer supported by the bearing, and then you lost lateral support, and so forth and so on. Let me point out to you that the video on the left, and I don't see where. Anyway, I have a video which would show you the behavior of this, and I don't see it on this slide, but it was on my PowerPoint. So there's basically what's going to show up here, unfortunately, is if you take a look at the failure on the left, which is the real building, and the failure on the right building, you would see a whole different condition. And here's what you would see. So this is the picture, and I turned this picture around, so the left side is where the springs are, the right side is where the springs are not, and if that building began to fail, the left side went down faster than the right side, which is not what you saw in reality in the real building. So that separated progressive collapse, which means, by the way, that their model was not accurate, nor correct. So this should have been a video that would show the failure of this thing, and I apologize that it's not showing that. But so the NIST approach, they had an excess of 5.5 inches moving at girder bearing support column 79, and those issues that led to that movement were, number one, non-composite of the main girders, which was pretty insignificant, quite frankly. Neglected thermal expansion of the concrete slab. They did not consider the expansion of the concrete slab, and yet the concrete slab is there. It's moving with the steel. And even if you said it was separated, there's a frictional component between the steel and the concrete, and it's going to move. And so there's a mu normal, which is the normal weight of that concrete acting down on it, and until you cause it to slip, it's going to be working with it. The separated connection modeling was a major factor in how they ended up with the 5.5 inches of movement, and the mixed white web flange stiffeners were also missed by them. So UAF structural approach was to use two modeling programs. We had quality control. We developed the nonlinear springs for the structural connections everywhere to ensure that we ended up with what the structure acted like instead of what the structure may not have acted like. We looked at both composite, partially composite, and non-composite response, which is significant in gravity loads, but not in terms of the thermal response. Floors 12 and 13 springs were examined, and we looked at thermal expansion of those systems. Sept 2000 floors 12 and 13, and floors 3 to 47 were in the process, has been modeled as a virtual system. And NIST fire models were used to examine what our results might have been through this process, and then we looked at the heat transfer, which was another fire model that we put together, which was pretty significant. The UAF research approach continued with a steel framing, so we have connections, column to beam, beam to girders, throughout this structure, and those are all modeled by nonlinear springs. And the reason we're doing that is because as the structure begins to fail, we want to be able to model and understand how those connectors are working interactively with the steel framing. We substructured the entire structural system so we could analyze fairly quickly potential failure mechanisms throughout this building to utilize and minimize computer time. Heat transfer was studied for the following. We looked at the floor covering, the welded wire fabric within the floor, stay-in-place forms. With the flutes of airspace between, we can treat it as insulated and non-insulated in that area between the floor framing. We looked at drop ceiling. We looked at that stagnant airspace between the drop ceiling and the steel system. We looked at fire protection versus no fire protection, and we looked at also equivalent concrete conductivity and thermal expansion, accounting for dolomite aggregate within the concrete deck, welded wire fabric, and the geometry for the section. Okay, I'm about there. Well, the NIST also didn't realize or made a mistake in not including the web stiffeners at the girder column 79, and so we did, and this is what our model on your left looks like. And so I wanted to just kind of look at and show you the sampling of what we did in terms of our connectors. We had a low deformation of this is a shear connector located at a spot on your right-hand side by STC. We gave it a name. We did that for lots of different ones. This is the abacus connection model that we're using. This shows you finite element-wise how it looks. This is a low moment rotation curve for it. This is a shear deformation curve that we'll have for it as well. This is a SAP model of all 3 to 47 stories. This is the view of the UAF SAP model using SAP 2000, and you'll notice that with the 5,142 kips acting as gravity load at the time this failure occurred, there was a displacement was 1.92 inches at column 79 instead of 5.5 inches. We also looked at all the material properties, and I've listed them here for you to look at briefly. A572 was a 50 KSI steel. Thermal conductivity was 35 BTUs per hour per degree Fahrenheit. We had a thermal strain, which is the same as NIST had recommended. We looked at the concrete behavior based upon what was used there. And so this kind of gives you an idea of, remember that 5,142 kips is what this thing would have loaded at. The NIST columns didn't reach higher than 392 degrees Fahrenheit based on NIST's report. Their argument was that it was all about expansion. So the NIST fires, here's what the fires we used for the temperature distribution. And column 79 through abacus gave me 1.85 inches of movement instead of 5.5. I have a comparative table here to give you an idea of floor framing steel connection springs. We modeled those. NIST only modeled part of them. Exterior steel framing connections were modeled both by us. NIST did not. Girder to column stiffener plates were used. NIST did not. Floor composites with beams, not girders. We both did those. Floors composite with beams and girders. We looked at them. They did not. Thermal expansion of the concrete deck. We looked at that. They did not. Thermal conductivity and expansion for material properties. We looked at them and they did not. Our thermal movement at column 79 was less than 2 inches. Therefore, our conclusions are the concrete floor diaphragm stiffness is insignificant, and with no shear connectors, frictional resistance to thermal expansion is not trivial. The thermal expansion for the concrete deck cannot be ignored, and it's likely that less than steel the value because it's based on the aggregate, 70% aggregate. The research team evaluated by considering airspace below, and I've already mentioned that, so I know I'm running out of time. NIST vertical collapse was not consistent with that of the actual collapse. The difference was primarily influenced by not modeling a significant portion of the structural framing. Remember, that's stiffer than the other, and so it moved a lot farther along. Matter of fact, the stiffest area within that system is around column 79. So what's next? We will finalize placing springs at every floor in SAP 2000 model. We will conduct progressive collapse by failure at the substation level, shock waves. We'll look at that by the falling debris from the towers. We'll look at radiant heat from towers 1 and 2. We'll examine the building's response for various columns being taken out. And we will initialize placing springs at every floor of the SAP 2000 model. Okay, that being said, I'm going to move to here. Did building 7 collapse from fires? And the answer is no. UAF finding shows that the girder bearing at column 79 moved less than 2 inches. It would not have been a problem It did not have a problem in lateral buckling, not using their fires. Thank you.
What does that mean? I can't tell you how important what you just heard is. Now, you may not have understood all of it, but what it means is that this is a direct challenge to the computer analysis that NIST did to prove their collapse by fire theory. They juggled this football for 7 years, hoping everybody would forget about it and go home and not talk about it anymore, because here is the worst example of a deception of all of 9/11, because it's so clear. This building, as you'll see in the evidentiary hearings tomorrow, dropped like a rock straight down uniformly, symmetrically into its own footprint in under 7 seconds at free fall acceleration. Dr. Hulsey just proved that that cannot happen by fire. That means all of academic institutions across this country and around the world have been lied to. And they probably knew this. Tomorrow we're going to talk about what can remove all 80 columns in this building that would allow it to fall at free fall. That is the second part of this discussion. But this particular study needs to go through the peer-reviewed process. It needs to be completed. We've got 6 to 8 months of additional finalizing, shoring up work that has to be done at the university with his PhD students. And then it goes out to the academic community, and it will change the game. It will be peer-reviewed. It will awaken architects and engineers across the country. Throughout academia, it'll become the most studied building failure in history. It's been hidden and suppressed so far, but it can't be after this is out. So NIST performed their own computer animation in an effort to prove their theory of this thermal destruction, expansion, which caused the destruction of this building. And as you can see, on the left we have the video. On the right is their computer animation. There is no similarity, as Tony began to describe. In fact, their own computer animation completely disproves their theory. Even the computer model begins to tip over, as any natural collapse would. You can see the vertical collapse we've been talking about here. They try to prove there's 400 structural steel connections failing every second in their computer model in order to get it to try to fall as fast and symmetrically as the video actually shows. But you see buckling actually in their computer model, which also we don't see on the video. To go into a greater effort to understand what couldn't have happened in this building for its destruction, I'd like to bring up one of the top forensic structural engineers in the country from the University of Alaska, Professor Leroy Hulsey, structural engineer, Ph.D. Professor Hulsey?
Good afternoon. Do I push this down?
No.
Okay. Good afternoon. It's a pleasure to be here today, and thank you all for giving me the opportunity to be here. Under forensic structural engineer up above, it says Las Vegas, Nevada. That's not true. Fairbanks, Alaska is true. So I want to just kind of give you a little bit of an insight of who I am and kind of give you some background before I get into this presentation. I'm actually also a licensed structural engineer. I have been in the business some 40 years. I've worked on, as an expert, the Avenues of America building, the United Nations building, the Dean Dome in North Carolina, and a number of other structures around the country. So what I'm bringing to this presentation is the fact that I've done a lot of work on structural investigations, and so when I was asked to do this, to investigate the collapse of the World Trade Center 7, I thought it was quite an honor, and I've put together a team that I feel is really, really good. Dr. Fang Xiao, who is a postdoctoral researcher who did his PhD under my work, and then Zili Kwan, who is a PhD student now, and because of this project, I've redirected his research effort, and he's going to be looking at fires on high-rise buildings, and particularly steel structures. So that being said, let me take you to this first slide and focus your attention onto the blue outline. And we're looking at the plan view of the floor 13. Column 79 is not identified there, but you see column 76 and 78. And if you remember that picture of the building falling a moment ago, that if we rotate this 180 degrees and put the blue on the left and the stuff on the right, that blue area represents the NIST's approximation of connections for this building. The portion on the left of this plan view, they chose not to put any of the connections into their finite element model, which indicates that the section to the left is much stiffer than the section to your right. Furthermore, they didn't approximate the stiffness of the connectors on the exterior port of the building. Now, what does that physically mean to you and I? What it means is when you heat up a bar, the bar is going to try to elongate. And it will elongate without resistance, no matter what, unless there's some place that's stiffer than another. If it's fixed on one end and free on the other, it's going to move to the right, imagining fixed being on your left. If I was to put fixed on your right and free on your left, it would expand to your left. Now, if I fix it on both ends, it can literally tear itself apart with a fairly low temperature. So here's the situation on this building. When NIST modeled it, they did not model it correctly because there are connections everywhere. And so that means part of this building was treated more stiff than the other part. And if remember when you saw the thing come down, what happened is part of the building was coming down differently than the other part. That should have given them a clue right away. That's not what really happened. Take a look at this picture right here. See that red line down? The left part is where they modeled the connections. The right part, they did not. So the left part, when it starts to fall, is coming down fairly rapidly, but the right part is really, really stiff. And so it's not anywhere simulating what really happened in the real building. So that immediately should have told them that this model that they were trying to use to argue that the fire brought this building down was wrong right away. And from the first time I saw this, I was wondering what in the world is wrong with this model. And it wasn't until a few weeks ago we identified the real cause of this. You know, and that's through this process because we've modeled every connection. So let's examine the NIST approach for a moment. They've said there's more than 5.5 inches of movement at that girder to push it off the bearing, and so that the column was no longer resisted there. Well, you can imagine that being real stiff on one side, the amount of movement that was occurring was going to accumulate over that length, whereas actually the more stiffer part is near column 79. It didn't move hardly at all. So the issues that led to that 5.5-inch movement primarily were due to the fact that they didn't model the connections properly. And there's some question in my mind about even in the place where they did model the connections, they were not connected and properly substructured within the model itself. And I realize I may be using words that you're not familiar with, and I apologize for that. But what I'm really trying to say is that in the real structure, they had bolts and they had these connections, putting beams to girders and so forth. And on part of their model, they didn't include those. On the other part, they did, or they attempted to. We did everywhere. So they also so the issues that led to the 5.5 inches of movement and more, it was actually more than that, was they treated the non-composite, the girders, as non-composite. In other words, what they did when they looked at the thermal expansion, they didn't include the concrete slab in it. That was totally wrong. They separated the connection modeling. That was wrong. They missed the wide flange stiffeners. That was wrong. So, so giving you kind of a comparative narrative of what we did versus what they did, our floor framing steel connections were addressed by using the word springs. That basically, there's some resistance to the bolt and how that is resisting movement up and down, and there's some resistance to rotation and all that kind of stuff. We addressed that in these connectors. So in this table, you'll see they did it partially, in other words, over part of the floor system. We did it everywhere. Exterior steel framing connections were included by us, but were not by them. In other words, there was a sense of stiffness that was not correct. Girder to column stiffener plates were included by us, not by them. The floor composite with beams, we included, we said they were composite. We also said they were not composite. We wanted to look at all extremes to make a comparison between whether we could simulate what they did or not. The floors with composite beams and girders were examined by us, yes, not by them. And by the way, I think you can imagine that even if they were not composite, the concrete deck is fairly heavy. It's going to be setting on the beams and the girders, and so to slide the concrete with respect to the steel, there's a lot of friction. And so it's going to take a huge amount of effort to make that happen, to slide without those two working together. And our analysis shows that that couldn't have happened. Okay? The thermal expansion of the concrete deck was included by us. It was not by them. Thermal conductivity expansion for the material properties, we included what we believe to be the aggregate that was used in the construction. And the aggregate type significantly affects the thermal conductivity and the thermal expansion of the concrete. So we tried to make sure that we had an understanding of what may have occurred truly on that day. The thermal horizontal movement of column 79 was, it was more than 5.5 inches. I gave them credit here. It was more than that. But it was less than 2 inches by us. And let me also share with you this. We had a quality control program on every single day. My students, my PhD, my doctoral graduate and my PhD student, we meet every single day. We talk about what we've done. We criticize each other's effort. We make sure that we can justify every piece scientifically. And then, and so as part of this, we use 2 different computer finite element programs, 2 different ones. And we did that for a reason. We cross-checked each other's work through looking at each other's models, and then we also ran them using 2 different programs. One of these gave us 1.9 some inches plus inches, and the other one was 1.85 inches instead of the 2 inches. That's why I said it's, so both programs gave us less than 2 inches.
Dr. Hulsey, let me ask you a question. You've listed here for us 8 or 10 very specific things that they didn't do or that they did incorrectly. Based on your own professional judgment, do you think that that falls within the realm of simple incompetence, or do you believe that this demonstrates a pattern that is so gross that it had to have been done intentionally?
I don't know the answer to that. I don't know how anybody could think that this was a cover-up and know anything about finite elements and know structural engineering to think that they could get away with that.
Right, but if one of your PhD students submitted this to you, would you have flunked them?
Yes.
We're going to go straight to this slide now, and I got to go on.
Okay. So my answer to you today is that the fire did not bring this building down. Thank you all for giving me the opportunity to present that.
Can we ask a question? Can we ask a question?
Yeah.
Would it be all right?
Yes.
Can't hear you.
I want to stress that the NIST report regarding the World Trade Center 7, have you studied the part of the report? At firm state that the collapse fell was due to the thermal expansion of the structural steel. And after he told that the World Trade Center 7 fell because of the fires provoked by the diesel fuel and from debris. Do you think that it is possible that it was there is a cause between a connection between the fire expansion and the fall of the World Trade Center 7? What do you think about this affirmation statement of NIST? Have you read this?
If I understood what you're saying correctly, I do not believe that there is any possibility that could have happened that way.
Let me ask this: if you could, on a scale of 1 to 100, what do you think the possibility is of this particular building failing with the data with regard to these specific fires? On a scale of 1 to 100, how probable do you think it is, or how possible do you think it is that this building could have collapsed simply because of the fires?
0.
Yeah. If you could, second. My reaction to what you've had to say is, of course. And in fact, as soon as you were given the problem of trying to just study, why this building went down, it seems like you didn't really need to do anything. You could have looked at the video and seen and come to a conclusion at that time. Wouldn't you agree that that's true?
I would agree that I knew that there was something wrong with that computer model.
Okay.
I did not know I did not know whether it was a fire-related issue or not.
All right. What I'm asking you is, you knew that was controlled demolition as soon as you saw it the first time.
I can't say that, and I won't even say that yet today.
Okay. So you were allowing for the possibility that building came down as a result of something other than controlled demolition. Is that what you're saying?
What I said from the day one when I took this on is that I may not be able to tell you what brought it down, but I'll tell you what didn't bring it down.
Okay, but I'm not, it seems to me that it's obvious simply from looking at the video that that's controlled demolition. Dan Rather didn't make that up, because he was being creative. He was reacting to his knowledge of life and his views of these things happening for as many times as he'd seen them. And I want to know if that was not your state of mind when you took on this problem.
Let me be very clear. I have a requirement to put away whatever my feelings might be and present to you pure science on what we're going to end up with. So we're not done with this. What we're going to look at are a lot of possible scenarios that may bring this building down, including pulling out columns as we move forth in the next few months. I will be able to tell you, when I get through this process, a lot more about this issue. And then it'll be based on a science answer, not on my feelings.